What is it up? Be rolling now, but we'll give it like, I don't know, a minute or two, um, just to make sure. What is it up? Okay. What is it up? Okay. All right. Okay.
And you just let me know when you want me to go. I'll wait for your signal.
All right. You got everything
I got
shared?
the live chat.
Okay.
Tanya, you're sharing, you said, the link. Can I be heard over here?
Yeah, I think you can. All right. I think we're good. So I guess we'll start. We have a wonderful guest today, Shawn from the Space Weather, I can't even talk today. Space Weather Prediction Center that we all love and adore so much. So he's gonna run us through some of the behind the scenes that goes on at SWPC and kind of talk about a little bit of the May 10th event. And we've all been waiting what, a month, 2 months for this. So we're all pretty thrilled about it. And then if any questions come in, hopefully we can get them answered either through the presentation or afterwards. So without further ado, I'll hand it over.
All right. Thanks, Mary Beth. Hey, I'm glad to be here, everybody. No problem at all. We enjoy doing talks when we get a chance to do them to not only educate the general public more about it, but, people that really rely on our information, whether it's sectors or critical infrastructure operators, whatever the case may be, or the auroral viewing community, because, we value your opinions out there. I've interfaced quite a bit with some of you regarding possibilities for improvement on some of the things on our page. So it's always valuable feedback, and we appreciate that. Not to mention, you've also identified some potential problems that are currently being investigated with one of our satellites. So it's always good to be connected with you all. That said, so I'm Shawn. I am the service coordinator here at the Space Weather Prediction Center in Boulder, Colorado. When I say here at the Space Weather Prediction Center, this is not my office. This is my office at home. I was in the office in Boulder today until a few hours ago when I came back here. But as the service coordinator, one of my jobs is education outreach. But among the many others is interfacing with the critical infrastructure operators, the technology users, our core partners and key customers that use our information to make decisions, to take actions. And as you're going to find out in the May storm, you can see how busy this role can get, how busy the forecaster life can be, as well as other folks within our SWPC organization. When I say SWPC, I'm saying Space Weather Prediction Center for short, SWPC. And of course, this all lies within our mission statement, and you see that here on the bottom: safeguarding society with actionable space weather information. That could not have been more true than in those big May events with the extreme geomagnetic storm. So who are we? Who do we have here? Well, we have all sorts of people, just not enough. We have a little over 70 personnel, a mix of federal employees such as myself, or college, Colorado State University employees that work for and with SWPC on kind of the research and science side. So we have this great mix from information technology folks, engineers. Yes, we get data right here on big giant dishes up on a hill outside of our Boulder building where we work for integration into some giant servers that occupy a huge office space. We have administrative folks, and then of course our forecasting staff. So quite a mix of folks are needed to do this work, and a lot more behind the scenes in the technology world to be able to get the information we need to do what we do here. Some of our important partners that we're working with, and it keeps growing. You can see many of them on here. This is probably not even close to all of them, but it continues to grow. The United States Air Force, my old profession for 22 years before I retired in 2007. And I've been doing regular meteorology or space weather since then. I guess I really didn't get into my background. Probably should bring that up really quick. So yeah, I was Air Force for 22 years. Most of that time was doing mainstream meteorology, but for 6 years, I was doing space weather, not only observations, but forecasting, and then even at higher levels after that. I retired in 2007 to go work for the United States Air Force, but as a civilian, did that for 5 years. And I decided, it's time to move again. We're used to moving around in my family because of the Air Force. Moved out to Hawaii, where I took a job with the National Weather Service. That's how I got into the Weather Service for a few years, doing observations, upper air launches, all focused on mainstream meteorology. But then a couple of years later, I got hired here. So in 2015, we moved here, where I was hired as a physical scientist to do space weather forecasting. And then back in August, I was lucky enough to be hired and promoted into this service coordinator position, which was new. They created it. It was really based off most of the project work I'd been doing, so I fit right in. It was the easiest job transition I've ever had in my life because I didn't have to learn anything new. I've been doing this pretty much the whole time I was here. But back to this list of folks, including the Air Force, we couldn't do this job without the Air Force. And as you're going to find out from an event on December 14th, nothing related to coronal mass ejections or anything. If it hadn't been for the Air Force and their fleet of radio telescopes monitoring the sun, we would have not have known of a major event that was going on of extreme significance. We're talking and starting to collaborate with international partners from the UK Met Office in England to the Bureau of Meteorology in Australia, let alone our NASA friends and Moon to Mars mission folks. These are the folks we interact with through mechanisms like Slack or through emails, collaborating, working together to make sure we have a common message. Because as you can imagine, when we're talking about G4 storms, we need the whole world to be on board and know that as well, because they're doing the same thing. They can't be advertising something completely opposite of that, nor should we. So that's why we collaborate with all these folks. Why do we care about space weather? Because the government has brought it forward to the forefront, as they should, because of past activities and events that have happened that have been very impactful to our technology and our way of life. And that reliance continues to grow. So the government has started to stress this over the last 10, 20 years. And you're going to see why all of this work, these bills, these executive orders, these congressional actions and giant working groups at the highest levels of our government have been so important and helped make a big success story of what happened in May. What exactly is space weather? Well, the easiest answer I can have is what's taking place on that giant ball of burning gas 93 million miles away, in that large vacuum of space between the sun and the earth, and ultimately at, here, and around our planet. Money. That's the main driving factor here. Is commerce could be impacted significantly if you had a catastrophic extreme space weather storm. Fortunately, that did not happen in May. Could it? Probably not to this level, but there may have been some issues if the problem wasn't being mitigated through interactions with us. But in the worst case scenario, if we experience one of those rare, catastrophic, no kidding, much stronger G5 level geomagnetic storms, or mix it in with a giant solar radiation storm that's bombarding satellites with energetic particles and making life miserable for satellite controllers and the electronic equipment on those satellites, then we're talking billions of dollars of potential loss here. Why? Because a geomagnetic storm may knock out the power, not just for a few blocks in a city, but not just for a county, not for even just a state. We're talking states would be impacted by a major power outage from something like a major extreme geomagnetic storm. And of course, we keep putting satellites into space. So the more of those look out there, the more there are chances for those to be disrupted or have problems due to extreme space weather storms, like a giant solar radiation storm, for instance. How do we do what we do? Well, we have our mainstream personnel around the Space Weather Prediction Center that I outlined earlier, but the forecast office, where I'm assigned to and work directly with, and still work rotating shifts in there in and when is needed, just like I did during the May event. We're staffed in there 24 hours, 7 days a week with our forecast staff, which when we're fully staffed has 11 forecasters that rotate through the various needed shifts. Myself is part of that group, our science operations officer, part of that group, and of course our operations chief. And this is what we're doing in there. We're not only monitoring data and systems and conducting analysis and forecasting, but the most important thing we do is the watches, warnings, and alerts, just like a regular terrestrial weather office. So us being part of the National Weather Service, we take great pride in the protection of lives and property. And yes, we do that when it comes to space weather. Not your life is not going to be physically impacted. I don't care if you're on top of Mount Everest, if you're that adventurous. You cannot be hurt physically by one of these storms. But the repercussions of an extreme space weather storm could impact you. And as you're going to find out, it led to the deaths of soldiers in the Mideast in 2003, unfortunately due to some communication issues. A lot of our partners are on the outline on the bottom left. That's not all of them. That's continuing to grow as well. And you'll know what all these things mean as I talk to them here later on. What are we forecasting? Well, many things, but the big three. The big three are what you see here because they equate to our NOAA space weather scale. So it's really about the impact. So when we're forecasting, we're really forecasting the impact. But what we're thinking about and what we're really doing is trying to understand and predict the space weather events that cause those impacts. So the scale is impact based, whether it's S, R, or G. So solar radiation storms is the S scale. That's the effect. HF radio blackouts, that's the R scale. That's the effect. And then geomagnetic storms is the G scale and effect. The underlying cause that we're really trying to predict and we put our probabilities out for are the solar energetic proton events, the solar flares. We do not do that for coronal mass ejections or coronal holes. And don't worry, if you don't know what that means, I'll be telling you here shortly. But we just don't have that science to predict whether a CME is going to erupt off the sun. So we don't do that, but we start to talk to it when we see them. And that's ultimately what we're predicting that leads to our geomagnetic storm forecast. So even though we don't predict the probability of the underlying cause, we are predicting the probability and chances and to what level that may get for the actual effect of the geomagnetic storm. So our solar cycle, why do we have these periods of escalated activity like we're having now? That's because the sun is rotating on average every 27 days. And because of that rotation, the polarities magnetically on the sun shift roughly every 11 years. And during that shift process, the sun kind of erupts in activity because the strong magnetic fields that generally are neutral during solar minimum, as things build up to solar maximum like we're in now, the sun becomes littered with strong embedded localized magnetic fields. And when they're strong enough, they reveal themselves as sunspots. Where are we at in the current solar cycle? Way above the original prediction. You can see here something that isn't shared normally publicly, but it's out there as an experimental product. We hope to have it operational and out there real soon on our webpage. But this is a glimpse of that. The pink shade on that plot is the original forecast for the solar cycle prediction. This was done by an international panel of scientific experts in this field before December of 2019. That was their original prediction. We are well above that, so much so that the satellite community and launch community and others that need long-range predictions of solar activity, we needed to modify this. So one of our top scientists in the building in SWPC went ahead and did some work with others and came up with this modified forecast. And you can see that's much more in line, and it gets adjusted every month as need be to keep things as current. But look at the black plot. That's where we're at. You're going to see a graphical post that I put out today showing and highlighting just how active this cycle has been just as of yesterday. Sunspots. So when these magnetic fields localize or strong enough, they reveal themselves as these giant sunspot clusters. 109 planet Earths fit across the center of the sun side by side, just across the center looking at us. So these sunspot groups, like you're seeing from just 2 days ago, they're massive. Region 3780 down there in the south in the left part of the sun, what we call the southwest quadrant, is huge, many Earth sizes in coverage. And what do we do as forecasters? We classify these sunspot groups. So those of you who are familiar with those classification schemes, you understand that. So if I say FKC, beta, gamma, delta, you know what that means. Other views would think I'm talking about a sorority or fraternity, perhaps. It's really a classification scheme. If you want to learn more about it, please go to our webpage, find out more, research it up, and you'll understand it all. And you can use one of our messages that we put out every day to get a better idea of what we're thinking of these groups. But we look at them not only structurally, but magnetically. So that multicolored plot on the bottom right is a magnetogram. An instrument in space on the Solar Dynamics Observatory, a NASA research satellite, is what we use for this. We also rely upon the Air Force solar observatories with their optical telescopes because they have the capability to magnetically map some regions of interest as well. So between all these things, that's what we really forecast our probability off of, is the magnetic complexity of these regions. What have they been doing as far as activity goes? Have they been flaring already? What have those been those levels? Are they decaying? Are they growing? Is there a lot of motion in there? All this is what ties into works to when we do our solar flare probability forecast. So despite the ominous look of region 3780 there, it's really not that magnetically challenging. It has been producing activity because there's a lot of strength there. There is some mixed polarities and things that we look for in there, but it could be a lot worse. Like back in May, that region was, imagine magnets twisted up, punching through the same magnet in multiple ways. That's how stressed up and mixed up the regions were back in early May. We don't have that right now, but that's not to say that it isn't capable of doing something, because it most certainly is. So what happens? What is it we're forecasting? Well, we're forecasting the chances for a solar flare, this giant burst of electromagnetic energy across much of the spectrum that we measure, but we measure them in X-rays. So we have to use a satellite in space, because thankfully our atmosphere protects us from harmful X-rays. So the GOES satellite, the one we rely upon for mainstream meteorology and all the clouds that you see on TV, has a space weather package on it. And one of the things it's measuring is X-ray flux. So when we see that plot begin to rise, and you can all see this on our page, we know that flare is in progress. And then we'll try to find the source with the imagery that's on the GOES satellite, or with our Air Force observatories and their flare reports for optical activity and other sources to identify the source. Because even though the source, the location of the flare does not matter for it to cause an HF radio degradation issue or blackout. Because what it does is, when that flare happens, the sunlit side of our planet is immediately exposed to it. So we see the flare like you see in this animation on the far left limb of the sun. The effect is immediate on the sunlit side of our planet. It's already made its 8-minute journey here. There's a lot of confusion out there, and people like to think, well, in 8 minutes is something going to happen. No, it's already here. We see it. So we can't warn on it. We can only predict the probability that they'll happen and how strong they might get to. So we alert when we see them. But there's unfortunately, no science yet to tell us a flare is imminent. We have clues and we'll watch, but no way to do that. So this location does not matter, but location is still important for a wide variety of other things, to include solar radiation storms that I'll talk about next. But solar radio blackouts, this is the underlying thing going on. We're communicating with, like, air traffic control, for example, directly on the phone. When we get to an R2, just a 2 level on our 1 through 5 scale, we're picking up the phone and we're talking to Oakland Air Traffic Control to let them know about this flare. Why? Because the aviation community flying across the ocean still relies upon HF radio as not only a backup that they have to have operational, but perhaps as their primary system if other ones aren't working as well or they're not connecting to something. So New York Air Traffic Control, we'd be calling them too, but right now they get our things directly. They always have them on display, and they're well aware. Plus, they can reach out to us at any time for any questions. But look at this flare, only an R2 from a year ago, back in May. This caused some issues with their New York Air Traffic Control. There was more than what I put on here. This is just an example. The summit side of Earth was exposed on the oceanic flight, and it happened to be a major issue. So this does cause problems, although there's other means to communicate during these activities for aviation. But sometimes when you combine a terrestrial weather event with a catastrophic, with a strong space weather event, then you can really exacerbate the problem. So the last solar cycle in September of 2017, we had the strongest solar flare of that previous cycle. At the time, we thought it was a high-end R3. I think since the new instrument's gone up, it's now being called potentially an R4. But either way, this flare happened at the same time hurricanes like Irma had already ravaged the Caribbean islands. FEMA and other emergency response personnel were deployed out to the islands trying to help people that had no power. They had no telephone lines because those are all ripped to shreds from the hurricane force winds. Cell phone towers are bent to heck and not inoperable, especially since there's no power as well. How are they communicating? Ham radio, high frequency voice modulation radio. They couldn't do it because most flares are very impulsive, meaning they last minutes, they're quick to rise, and then they come down. This one lasted hours. It was a long duration event. So this really doubly exacerbated the problem that was being dealt with. So this was very impactful. People that were in need of emergency response or to contact loved ones couldn't even do it. So this was quite the issue. Could this happen again? Absolutely. And with climate change going on, this even is more of a potential problem with the power grid, as you're going to find out. So solar flares, here's a plot from flares in February, very impulsive ones here. All 3 of these trio level of flares, even though we got to the R3 levels 3 times, short duration impacts to aviation, most certainly, but we were mainly on the dark side during a lot of these flares. But this is where being educated and smart helps, because what happened during these flares is a broadcast meteorologist started correlating the flares for a major cell phone problem that had happened. Guess what? We got calls. not only from normal users of that, but from the Pentagon, wondering, was it the solar flares that are causing this outage? So we had a message that's what you see in the bottom left here. We had a message out and say, no, this was not the cause of any cell phone outage based off the knowledge that we have and know. In the end, about a day later, it turns out they fessed up that it was some kind of software upgrade that didn't work out exactly correctly as needed the first time. So it's always important to know. So if you start hearing about space weather or potentially an impact, go to us, go to our webpage, find out what's really going on, make sure there's some logic behind the reasoning there, or to find out what the real scoop is, because you can't always believe everything you see on the media and social media, as I'm sure many of you know. So what else are we looking for? Well, this is something we can't predict, but we're constantly watching for it. This is something called a radio burst. So back on December 14th, a date that's going to live in kind of space weather infamy at this point, because it became something that was not new, but was really unprecedented at the time. What did the sun do on that day? Well, it did this thing called a radio burst. So the sun is this giant radio transmitter as well at all times. On all frequencies, there's energy from the sun. The Air Force Solar Observatories monitor 8 discrete frequencies. By discrete, I mean there's specific frequencies that they're monitoring. One of those falls in the VHF realm, so above high frequency. It's very high frequency. Another one in the ultra high frequency. This is what aviation communicates on domestically across the United States for line of sight communication with air traffic control. So as they're orbiting or taking off or coming in for landings, they are talking usually via VHF or UHF channels. When this radio burst happened on the sun, which is a dramatic increase in radio energy on these frequencies, it happened to be on those same frequencies the airlines are operating on. It got so bad that it got to 10,000 times over the normal background level. So the sun became a jammer. The planes could not talk to air traffic control from the East Coast all the way up to the northwest coast of our country. So pretty much across most of the United States for up to 8 minutes in Seattle. It got so bad there that they started tossing around the words ATC0. What does that mean? I don't have to tell you what it means. I just have to tell you the last time that was declared was the 9/11 terrorist attacks. It means shutting down airspace. It was that bad because it was not only affecting their frequencies to talk on, even other things that were on those frequencies were being impacted. So what happened here? A lot came together at just an inopportune time. So it's December 14th. We're near the solstice. The sun is lower in the sky. The sun has to be in the background for this to be an effective thing. If the sun was overhead, this may not have been nearly as impactful. So it's lower in the sky, and these planes are orbiting lower in the sky, so they keep crossing the sun. And therefore, they couldn't talk to each other for such extended periods of time. As the Seattle controllers and meteorologists that sport out there told us that if this had lasted some minutes longer, they probably would have went ahead and shut down airspace anyway for flight safety issues. So yeah, space weather is impactful. And even when we thought something like this was unprecedented, guess what? It happened again. May 9th, unrelated to the geomagnetic storm, the sun lit off another one of these on those same frequencies to nearly the same strength level. The difference was it was May, the sun was a lot higher in the sky, but even more importantly, it happened while the sun was over the Atlantic Ocean. We were still in the dark here, even on the East Coast. So that time it wasn't as impactful. But yeah, space weather is important. And in today's world, we have to know what's going on immediately. So we started messaging this to the air traffic community as soon as we started realizing this was going on. And even other entities like Cyber Command needs to know, because they need to know, is this a cyber attack? The entities need to know, is this just a technological malfunction? What do we do here? It's a good thing they did nothing. They just had to wait it out. But as you can see, this can become the national level prominence and concern pretty quickly. What's another thing we're forecasting is these solar radiation storms, these gigantic releases of solar energetic particles in the form of protons. So it's the protons that really cause these, and heavy ions and such things. So the protons are what we're measuring. Now, this gets really complicated pretty quickly. You know, as a rural chasing community, this isn't something you're ever really going to have to deal with. But for your interest, this is something you may want to watch, especially when we're going back to the moon, because I know you're all enthusiasts like me here of things like that. This is something we're going to be dealing with heavily, not only now for the benefit of the health of the astronauts on the space station and the general satellite operational reliability of those spacecraft out there. But when we go back to the moon, those 4 human beings on that Orion capsule, they are totally at risk to be exposed to these events because they're not behind our protective magnetic barrier, and they certainly are outside the realms of our atmosphere. So we will have a forecaster or 2 deployed to Houston Mission Control during those Artemis missions because of the importance to their lives in this case. So we forecast the probability of these, and this is where location does matter. So I said the flare don't matter. It could be around the sun. That sunspot region that's responsible for it might not even be visible yet, but if this detector sees it, the atmosphere sees it and it's exposed to it. These are different. These have had to rotate normally to the right side of the sun, what we call the west side. Not exactly to the limb, but before the limb and not near center disk. That's kind of the prime area where these can come out from the sun because they're locked onto magnetic field lines that come out from the sun and then curve about 3 solar radii from the sun. So these spiral around those. The only way those can cross those magnetic field lines is with tremendous force. So when these regions get to the right side, that western side of the sun, that's when they're directly in line with Earth, actually, because of that curve. So that's when they can arrive here as fast as 15 to 20 minutes. Otherwise, it could take some hours, or it can be even 24 hours or even longer, perhaps. But we have been affected by these storms. So from activity this cycle from the other side of the sun. So just a few weeks ago, we had a coronal mass ejection that happened on the far side of the sun, going the other direction. But that force crossed those magnetic field lines with those protons, and they actually arrived here as a pretty notable storm. So this is what, we can't forecast that. So sometimes we have to just deal with an issue that comes up, but we just don't have the technology to expect it. So when we have these storms going on, we are communicating with NASA directly on the phone. We do this every day regardless. But when these start to pick up, or the stronger solar flares, we're picking up the phone and talking to the solar radiation analysis group that supports the astronauts' health right there at NASA. Launch communities, they will not launch into some of these events depending on their strength because they can't risk, as it gets higher into the atmosphere, that rocket to be exposed to these particles, because if they get in there in just the right way, they can affect the electronic component, cause an anomalous hiccup at the wrong time. And as you can imagine, when you're going to fast speeds like that, it doesn't take much to go off course and cause stress on the platform, and you have a catastrophic failure of the spacecraft, and it basically comes apart. Before I get into the next big thing, let's not forget about coronal holes. Nothing to do with solar flares, but as you're coming down from a solar cycle peak, as you start to work your way down that plot towards solar minimum, that's the prime time for these events. And as an auroral viewing community and hobbyists and enthusiasts, you want to know about these because these can be very large and prolific like you're seeing here on this animation, and they can last some rotations. So months they can last. And this is a great way to do a long-range prediction of perhaps seeing the aurora, especially in the northern tier states, is when these are going to be back around in what we call geoeffective, meaning they could cause that increased solar wind that increases that geomagnetic response. We usually do not see above G3 with these events. It's kind of rare to even get the G3, but they can get pretty strong. Last solar cycle, we came close to G4 a few times with some of these, and we certainly had a few G3s. We've got some long-range predictions that are based off recurrence. Recurrence is basically our climatology. What happened one rotation ago? Is it likely to happen again this rotation? I put on this kind of the AP that we're forecasting in these long-range forecasts, even though that one says the U.S. Air Force, that's actually coming from us because we put one together and then they take it and they put it to their needs and we just share it on our page because it's a collaborative effort. So if you look at those AP numbers on that forecast, you find them on those products, that 27-day and that 45-day. Look at the AP number. If it's a 5, we're generally looking at quiet. If it's 8 to a 12, it's probably a KP of 3. It's not a direct relationship, by the way. This is just a rule of thumb for you. AP of 12 to 18, maybe we're at the KP of 4. Okay, that's starting to be notable, perhaps. And then you get to G1 and potentially G2. So just a long-range product for you to look at that we do on a weekly basis. So let's go back to the big ones. So we've talked about the other big two. Here's the big third, the coronal mass ejections and their relationship to geomagnetic storms. So these are the giant releases of coronal material in the form of billions of tons of it. But even more importantly, there's a strong localized magnetic field stretching out from the sun into space that eventually could reach Earth if it's aimed our direction. The fastest these can get here is about 15 hours, we think. Historically, we know of at least 18. But usually they can take 2 to 4 days. The events we had in May, they got here in over a day, but a little less than 2 days. So they were kind of in there, but not nearly close to the speed that we would expect with the ones that could get here in 15 to 18 hours. So when we see these CMEs, now we get busy trying to model and fit these things, as we call it, to ingest it into one of our models called the WSA Enlo model, which many of you are probably familiar with and know how to read and look at. That is, we'll do a number of these model runs to determine what we think the best solution is. And then that's what we'll go with and put our forecast out. So you've seen over the, each day now since Monday or something, we've been putting out a G2 watch, G2 watch, G2 watch. We'll talk about that at the end, but of why that is and kind of the uncertainty that goes along with that. Some though, like the one on the bottom right you're seeing here, are clearly going either away from Earth or directly towards Earth, right? So the stronger these events, it's a little easier to interpret. But even the one that's the big one in the middle, that may not actually impact Earth. It's very difficult to model these subjectively because we have to focus on the bulk plasma material. We don't look at the shock front because the model's already trying to account for that. So there's another level of uncertainty that can lead to our ability to give a really good confident forecast. So we put out, based off that analysis, we'll adjust our forecast, we'll make the new 3-day forecast, and we may put out a watch like we just talked about with the G2 watches. Now we have to wait. We have to wait for that 92 million mile journey to the spacecraft that's 1 million miles from Earth. That's when we start to look at warnings. So when we see arrivals out there of these coronal mass ejections, we may already fire out a warning or warnings, depending on the strength we're expecting. And then I'll get to when we put out the alert. So that spacecraft that's out there, the ACE, which is the NASA research satellite, and the Discover spacecraft, which is ours, a NOAA platform. These are what monitoring the real-time solar wind out there. And you, as auroral enthusiasts and chasers, are going to want to watch and monitor this real-time solar wind product. So let's talk about that for a minute. So we have several things on here, and this is all on our webpage. I'm showing you exactly where to go to it if you don't know. And this is where magnetism becomes very important. Solar wind speed, that yellow plot, is in kilometers per second. The normal background level of the solar wind is somewhere around 350 to 400 kilometers per second. Sometimes it can get lower than that. When we see jumps from what's normal, okay, there's something changing there, right? We get to over 450, it could be a coronal hole or a CME potentially. The other thing we're looking at is that magnetic field strength, the top plot with the white and the red lines. So the white line indicates the interplanetary magnetic field, IMF, strength, and it's measured in nanoteslas. Normally that background is sitting around 5 nanotesla, give or take. You start to see jumps up to 10, that's notable. That might be a KP4, potentially even a G1, depending on what happens. And that's only just double. The higher you go up that level of intensity and strength, the more likely we're going to have some reaction here at Earth. But here's the other problem. We have to know the orientation. That's the red line. Is it pointed south or is it pointed north? Is it above that dash line or is it below that dash line? So this is where magnets become important. So Earth's magnetic field comes out the bottom of our planet and goes into the top. So it's pointed north. It's thumbs up. Along comes a CME from the sun. If it's pointed the same direction as Earth, yeah, you're going to get initial wallop, some initial reaction regardless. There's infiltrations going on and substorms and all these things that can happen. But you really need it to be opposite so the magnets connect. Now you're literally connected to the sun, that solar wind field, and that magnetic energy in there. That's when things really escalate. That's when we rapidly increase and you start to get to the storm strengths that we had potentially in May that become quite possible in those events. So this is something you really want to monitor because this is your best indicator of when things are favorable. If you see things start to turn south and we're strong magnetically, the wind speeds up, perhaps even. It doesn't even have to be, but you really want that to be as well. Now it's time. That's how you can kind of monitor minute by minute of the changes going on. Okay, now it's time for me to drive 20 miles outside of the city lights because things are turning favorable. It can easily go back and forth, but that might be when the aurora begins to spin up as well. Geomagnetic storms. This is what we focus on here in the forecast office. It's not the aurora, unfortunately. We kind of leave that to private enterprises and commercial people that want to, have a product to sell consumers, right? We stay out of that. What we're focused on is the impact from these storms. That's why we don't do aurora forecasting. We have tools out there like the Aviation model because that drives some of the potential impacts you're seeing listed out on here. So the geomagnetic storm can create a wide litany of issues to deal with, whether it's HF problems as well, which happened significantly in early May with that storm, by the way, and we'll talk about that eventually as well. Satellite communication issues, GPS accuracy, the power grid becomes impacted. These things eventually can cause electronic charges to build up on spacecraft in the form of some other particles that we're forecasting, like electrons, just a wide variety of things. This is what messes up the atmosphere out there, that ionosphere. When you get to the strength of storm that we had for over 24 hours in May, that changes things. We even had a third Van Allen radiation belt form as a result of that storm. Some of you may have heard about that. There's still other things that are going on from that storm to the research scientists' delight because they're able to find out and learn a lot more at this point. But we focus on the things you see here on the bottom. So we communicate with the users that need and control that critical infrastructure or technology that we rely upon so much today. One of the things we're doing to help with the industry, especially the power grid, is what are these geomagnetic storms doing with the current that they induce here on our planet? So there's always a natural current. There's one flowing right now between all of us. That's always there because of the interactions from the normal solar wind and our geomagnetic field here, our magnetic barrier. But you start to increase that level of geomagnetic deflections and responses that cause the stormings, that current can intensify quite dramatically and quickly. So what the power grid is concerned about is currents that build up on their high voltage transmission lines. So one of the most important phone calls, perhaps the most important phone call we make out of the Space Weather Prediction Center, is a hotline call to most of the power grid of North America. We do that at just a G3. And I'll talk in more detail about that in a minute, but let's go back to this model. So something the power grid really wants is not to know what the planetary KP number is. That doesn't necessarily do them any good, or certainly the G scale. They want to know what this means for amps on their high voltage transmission lines. So the best thing we have to offer to them over the last few years that has been developed is this geoelectric field model. And this gives an idea of volts per kilometer. By the way, this is normally in millivolts. So thousands of a volt. When you get to just 1 volt per kilometer, that's notable. Some of those power grid operators, transmission reliability centers are noticing stuff on their system. You get to 10 volts per kilometer, that's effectual. They're dealing with an issue. You get to 12 volts per kilometer, you have potential to be impactful. You get to higher than that, you've just increased dramatically the likelihood of some kind of bulk transmission failure, meaning power outage for hundreds of thousands of people. So that's what we're concerned about here. That's why we communicate so forcefully with the power grid. And I'll explain more about how that works. But this is just another thing for you to have as a tool, give you an idea. It's not a direct relationship because there's a lot that goes into this model. What's the orientation of the high voltage transmission lines? Are they east to west, north to south? What's their proximity to salt water? What's the conductivity of the ground and the underlying surface? But it is another tool for you to use to get an idea of, wow, if there's a lot of potential current on these systems, perhaps the sky is lighting up a lot better chance here further south than it might normally be in my area. So this is just another thing to kind of watch for. Just an idea. Like I said, there's no proven direct relationship, but it's another tool for you. By the way, we'll talk about it later, but the storm in 1989, based off this model now and what we could put into it from past events, this is what took down the power in 2/3 of Quebec, Canada in 90 seconds from the CME arrival. So the time that CME arrived, activity escalated. 90 seconds later, the lights went dark in Quebec, Canada. This is what burned and destroyed some transformers in New Jersey and damaged other ones throughout the northeast part of our country. How bad could it get? Well, this is an idea from the United States Geologic Survey, which has done a lot of these surveys for us and incorporated into our model, and who we rely upon, by the way, for the magnetometer measurements to help determine geomagnetic response levels. We're talking well beyond 10 volts here, in the order of close to 100 volts potentially in some of the worst case storms historically. Now, how they figured all this out, I don't know. I think this is also a total voltage, so it's not just about induced currents, but either way you look at it, North Dakota, Minneapolis, to the Minnesota regions, upper Northeast, down to the Tennessee Valley, these are the areas that are prone to these geoelectric fields more so than other parts of our country. What's the normal sequence of events? What do you want to be looking for? What's the order? Well, we see a solar flare. We talked about, we predict the probability they'll happen, but we have no way of warning on them because we don't know when they're imminent, so we alert. We alert at the R2 level. So for those of you who know X-ray flux, that's an M5 flare or higher. We send out that alert. We make those phone calls associated with that alert. Next thing we're immediately doing is looking to, do we need to put a warning out for an S1 storm or greater? If we do, we issue it. Then we put the alerts. Each and every single level that we hit. S1, we hit S2, there's another alert, all the way up through S5. The other thing that we're doing is now we're looking to see, are we going to see a coronal mass ejection leaving the sun in our coronagraph 1 million miles from us? Unfortunately, later this year, we'll also have one right near Earth on the latest GOES satellite that went up. That'll probably become our primary platform for that as we can use it. Then we determined we need to put out watches. And then we wait, right? We wait for that arrival 1 million miles from Earth to put out warnings. And then we'll alert as the activity spins up and reaches those estimated levels. This is something I've talked to Tanya about, is we do not have publicly available our estimated real-time KP index because it's pre-decisional. We have to wait and have a forecaster verify the activity because there's so many things that can be wrong with that data. So we don't put that out to the general public because we don't know for sure how valid it is yet. We make that decision, and that's how you see the KP numbers come out. So maybe down in the future, we'll have a way to make things more quickly for you. Maybe instead of waiting every 3 hours, maybe we can do it in 60 minutes, maybe 30 minutes, maybe less. But that's stuff we're looking at doing for an improvement. Because not only does the Aurora View community want to know that, others want to know that. What are we doing? What did we do in May? What did we do during normal times? Well, this is the kind of direct support we're doing to the operators of our critical infrastructure and all the technologies that we rely upon. This is the routine stuff here. This isn't even including the things that we were doing for the events in May. So we're always talking to the U.S. Air Force every day, several times a day. Why? Because they do exactly what we do, but they tailor it to Department of Defense needs. Top secret stuff, the secret world. We focus on the commercial side of things here at SWPC, but they take our forecast and they tailor it to those needs. They don't create their own, they use ours. That's why there's such a strong collaboration there. That's why we have an Air Force liaison officer always assigned to us here at SWPC. Space launch, communicate with them. If there's a launch going up and they let us know about it, and they want us to let them know if we're having a certain level of flare or a radiation storm potential or seeing things, they want us to call them. They want to be notified. So we'll do that direct support. NASA SHRAG, the radiation analysis group, talking to them. You can list it all. I don't have to spell them out for you here, but G3, that's when we pick up that hotline call and talk to the North American Power Grid. I'll give you a lot more detail about that and why we were very successful in May of not having a problem with electric power. FEMA, we get to the 4 levels on our scale on the radiation storms and Geomagnetic. Now we're talking to FEMA. FEMA wants to know. State emergency watch centers are going to start to know. If they're not already subscribed to that and getting it, they get it down from FEMA. When we get to the 4 levels, FEMA then sends that downward to the more localized watch centers and the other FEMA regions and more who all get that information. So in the past, we've had a problem where people have been getting that and they don't even know what it means. So that's a big campaign I've been working on and others have been working on here over the last years, is to get them smarter so they know what that means when they get it. So instead of trying to figure it out, they can act on it. That was another success story in May because that has happened now. They're all becoming much brighter about it and they know what it means. They know what to do with it. And for that event, we were talking to the National Security Council in the White House Situation Room because we did get to a G5, right? So the Biden administration was aware and monitoring the situation. If you heard that on the news, that's what that was about, because they wanted to be ready to take action in case there was a bulk transmission failure across many states, say in the Northeast or upper Midwest. So let's go over this really quickly again about kind of the order of events. Let's just use an event back in March. So this particular event, I happen to be working the evening shift, which goes till 1 in the morning. And these sunspot group down to the south and the one to the north. The one to the north doesn't look like much, right? So you'd expect the most of the activity from the south. But both of these lit up in flares, strong enough to level where I had alert on them. And I send the alert out and I ran our little proton prediction model. Mind you, those are not in favorable locations for a radiation storm, but they did reach the intensity of concern. So that model came back with something like a 50% chance of a radiation storm. So when the overnight shift came in and I'm briefing all this to him as he relieves me, he's like, yeah, we're probably going to get it. Because, I firmly agreed. So sure as heck, later on, energetic protons arrived. So it crossed those magnetic field lines. It made its way over. It was energetic enough. And this is the CME that showed up in the coronagraph imagery that energized those particles, allowed them to cross those magnetic field lines. Of course, we have to wait for that imagery. That isn't instantaneous like the data is we're getting on the GOES satellite. So then he started analyzing the coronal mass ejection now, and he's running through his models, and he says, hey, you know what? I think we're going to get hit by a CME. So then he puts out the appropriate watch. I don't remember what we put out for that event. And then we sit and wait for the CME to arrive. And here you can see the data on that real-time solar wind plot of when the CME arrived, what the geoelectric field model started to show. We got to over a volt per kilometer up in Canada with that event. So they were noticing it. They were spinning procedures up just in case they had to take some kind of notable action to prevent transformers from overheating. Nothing happened. Well mitigated easily. We didn't reach that extraordinary level, but it escalated quickly. We went through all levels up to G4, just didn't reach a G5 with that one. And by now you've been reading the stuff in the bottom. Yes, we're going through all these over and over and over again, all these direct decision support contacts and as how needed. Notable space weather events from the past. Well, the Carrington event. All right, most of you probably know that word or what are relatable to it. For those that you don't, back in the year 1859, an astronomer named Richard Carrington was observing the sun. He was drawing a massive sunspot complex, very similar, by the way, to the one responsible for the event in May. Anyway, he happened to notice two bright white lights show up around the photospheric bright white light of the sun that he was already looking at. That was extraordinary. It's very rare. It's called a white light flare. And he put it on his drawing. 18 hours later, the sky lit up with the aurora like we saw back in May. So much so, other places in the world. Remember, we didn't have the digital technology that we have today. People saw the aurora through their phone and pictures. They didn't necessarily with the eye. Back then, they were seeing it with the eye at these levels that people were seeing at with just their phones, perhaps. Very strong event. It caused problems with the batteries operating the telegraph systems back then. That was the main technology we had of the time. Sparks flying, fires started. There's a documented conversation between two of these operators on their slapping their metal plates together, call them diddy boppers, that they started talking about, let's disconnect our batteries. They did. There was still a signal. They could still carry on a conversation. That's what we don't want to see build up on the high voltage transmission lines today. That would be potentially catastrophic. That's why the government has been doing so much work over the last 10 to 20 years and why we continue to do what we do. You can see we already talked about 1989. You can see the tragic event in 2002. 3 soldiers killed because of a critical communication need. They were not able to get it because of a space weather event. So obviously the military has high concerns for these, just as we do for normal communication needs. The storms in 2003, the last time we reached a G5. Last time. That was much more impactful. You can see power outages happen in other countries. We had some anomalies and issues here, but no bulk transmission failure. Satellite losses. That storm also had a major radiation storm going on. We did not have that with this event. It was just a minor one. Satellites burning up in the atmosphere in February of 2022 because of a very minor storm, barely even a minor geomagnetic storm. Even today, because of the wild west of space, launches going up, all sorts of users of satellites throwing things up there. Today, once again, I was just contacted by another company out there that clearly is not space weather smart, but they're working on stuff going to the moon. So they're reaching out now, as they should be, to understand this better so they know what to look for and do. It's hard for us to chase that. So we need to get people smarter so they come to us, know to come to us, so we can help them out and they can avoid any big problems. There was a big event back in 2012 that they think was Carrington level event that went sideways from the sun. We know it was probably Carrington level event because there was a satellite over there at the time that was able to measure. In this case here, we had one went into back in March of last year, was opposite side of the sun. It was at Carrington level speeds. It also caused a radiation storm here at Earth as it crossed all those magnetic field lines. Now, those of you who know the WSA Enlow model on the bottom plot on the right, that bulk area of concentrated kind of gray and red material, that's going the other direction from Earth. We're on the right. That crossed a lot of magnetic field lines to cause that storm here at Earth. Could that have been a Carrington level event? We don't know because there wasn't a spacecraft to measure it. It's possible. So this solar cycle has been pretty exciting and active, even though they haven't necessarily been aimed always at Earth. So let's talk about the May events. So here's the sunspots that were on the sun back in May that we're monitoring. The one up to the north that's about to rotate off right there, and then the loop recirculates. That one up to the north was causing a lot of flares. R2s, R3 level events, but no CMEs. It did not launch any CMEs. The one down south that started to build up, let's see if I can get play again here. Let's go back. The one down south, on the other hand, once it started to flare, it was producing coronal mass ejections. We just don't know why that happens, why one might do that or one set compared to the other. But it clearly had a lot of energy. It grew pretty substantial. I told you how mixed up magnetically that region was. So when it started launching CMEs, it was back to back. That means several a day. And they were all kind of aimed in our general direction. So we're forecasting flare probabilities here, looking at the chances for radiation storms. You can see how this region changed. This is a loop I put together over the course of something like almost the whole solar rotation there. Let's play that again. Cooperate for me there. Size of Earth compared to this group, you can see, just imagine magnets twisted when popping through other magnets here of all these dynamic changes going on. We got to this stage right in towards the end of this loop. That's when it really was launching off these CMEs that were aimed towards Earth, that we're all evaluating every single one of them in our modeling. We started messaging about this because we knew this was getting fairly prolific. Industry, the press and the media, technological users, companies that support aviation that have been hired to do so, we're using this product right here. I saw it briefed recently at a federal aviation administration. And this is what that I'd actually put together to out there to inform people, just kind of let them know, hey, here's your chance to look at the sun. There's, if you have a safe means of doing it, it's active, pay attention over the next few days. And sure as heck, then it started releasing these CMEs. But this alerted one of these companies to, hey, there's something going on more than usual. So not only are monitoring our normal products, but they started monitoring these graphical things we've been working hard to put out more recently. And yeah, it was lighting up in flares. You can see how these were starting to happen. Those anomalies you see around the sun on this imagery are because the enhanced field got so bright it kind of messed with the imagery sensor a little bit. But these fairly prolific flares, and then we're looking for the chances for these CMEs to erupt from the sun. But meanwhile, we started talking about these flares, how the activity is increasing, our probabilities are going up. Once again, these were showing up in the press and the media, and operational users were using this information. Then we're analyzing all these CMEs. This is not all of them, by the way, but you can see how they were blasting right towards Earth. We knew these were facing us. We knew where they were coming from. Sometimes it's not so clear and we're not sure. There was no doubt, thanks to the radio observatories from the Air Force. We knew and had other signatures that tell us these are probably Earth directed as well. So our forecasters get busy and they're forecasting these. Originally, they were looking at a G3 potential with these CMEs, or the initial batch of these CMEs arriving. So here's a story. Well, I'll save that for later. So they put out the G3 watch. That went out over 24 hours before the storm arrived. So I think it was Thursday morning. We noticed that there was a G3 watch out. And I say notice because I was involved. I guess I'll tell the story here now. So I was involved down in Denver. There was actually, believe it or not, a national government level extreme space weather tabletop exercise going on. So our director and our program coordinator were deployed over to the Washington, D.C. area, working directly with FEMA National and all the governmental departmental heads that were involved as that exercise. I was deployed down to Denver to FEMA Region 8 because they were the participant region in this exercise. We're there. We see that a G3 watch goes out the second day of the exercise. It was a 2-day exercise that morning. So I'm seeing why that is, and I'm like, this has potential to be something stronger. I better brief and do a real-time interruption here. So that's what I did. My colleagues did it over there as well in DC. By noon, this got upgraded to a G4 watch. Now the forecasters clearly had more confidence because we not issued this level of watch since the year 2005. Now we know something serious is brewing. I'm talking to the forecast office, just as our director and others are, to understand exactly what they're looking at. So by noon, I informed them all we're up to a G4. Potentially, this could be a G5 event. So even though we pressed on with the exercise because we only had a few hours left, now they're getting real-time information. FEMA could not have been better prepared if we had had some kind of catastrophic collapse of the power grid because of our happened to be deployed to them for an exercise. How remarkable is that? So that's all Thursday. So now we're waiting, right? We got to wait for these CMEs to arrive. They were only going about 1,000 kilometers per second, the fastest one, by the way. So we had some time here. So what happens Friday morning? All right. For one, I was supposed to be having the day off on Friday, but instead I'm going to the office, obviously, because that's my role. I got to be involved here. We got significant weather going on. So we have a lot of things already happening. FEMA's already getting briefed because of the G4 watch. They're already communicating with FEMA, not only in place, but even afterwards. The White House Situation Room, the National Security Council, are starting to get briefed because they're asking about it, because they're hearing about it. So we're talking to them already. We're making all these other calls and talking to things as needed for any other activity. But here's the difference with this event. So that Friday morning, we're getting together and we're preparing, we're discussing the situation. So that NERC hotline call, we do that only for a warning and alert. So we reach the level, we call them. We put the warning out for a G3 or higher, we call them. That's only 15 to 45 minutes of lead time. That's a scripted call. After the roll call, where all the reliability coordinators, close to 20 of them for the whole interconnected grid, get on that phone call and then to disseminate that information to the 3,000 plus transmission operation centers out there, those 18 entities get on that call. It's scripted. There's a roll call and then the call is over in less than 5 minutes because we have to stick to the script. We read the warning, we get off, they ask questions first, and then we get off. We don't solicit information from them. This was different. I called our NERC contact. It's the North American Electrical Reliability Coordination. They're the ones that have responsibility for the entire power grid of North America. I contacted him and said, hey, look, we've got a high confidence level here in this G4 watch that you've probably seen about. What do you think about doing that hotline call now? And he said, great idea, do it. So I walked across the room and initiated the hotline call. Normally 5 minutes after the roll call, this went on for over 15 minutes because it was an opportunity for them not only to learn, here's what we're expecting. We have high confidence. You're going to see this thing called a sudden impulse. We won't get into that. As the shock arrives, you'll see activity escalate. This could get very rapid. G4 is our top watch. We have a great chance for a G5 here. And then they asked a lot of questions. They got ready. Based off that phone call, some of them started spinning up transformers that aren't normally active. They got them ready and operational. They got high voltage transmission lines that are normally ferrying less current and voltage, ready to ferry more. Why? Because now there's potential for things to overheat. And if they overheat, they want to have a plan to be able to deflect the energy, send it somewhere else so things can cool down. Because of that 6 hours of lead time they got with that additional phone call we don't normally provide, they were able to do those actions and be ready. So they were able and prepared to take action as the storm hit and progressed and rapidly escalated because we jumped quickly up to G4, eventually to G5, and we hit this for over 24 hours, these G4 and G5 levels of activity. Meanwhile, we're involved in so much more. Additional phone calls. I'm talking to all the FEMA regions. They wanted a phone call specifically outside the national one to understand more. State watch centers up in the northeast part of the country that I'd interfaced with recently. They wanted to talk. The communication industries executives, Comcast, Xfinity, Verizon, all those types of peoples, they wanted a phone call. I was talking to them to provide them situational support. Why? The satellites they rely upon. Why? Communication isn't going to be a satellite comm issue. You probably heard about Elon Musk advertising about his Starlink system. They were struggling. Anything in low Earth orbit was really struggling during that storm to maintain orbital integrity. Why were they able to do it? Because of the information from us, the interactions we built up, that decision support we can now provide so that they're ready, they're informed, and they're ready to take action, have a plan in place for when it happens. Our media engagement was overwhelming. Maybe some of you got on this call, I don't know. But in that morning, right after that hotline call, we had this call was scheduled. It ended up being close to 1,400 people got on that phone call. And this was conveying information for the press and media, but operational sector users also got on that phone call to include elements of the power grid, aviation industry, satellite community. Many of them were on this phone call as well. So it was a great way to communicate everything we possibly could about that storm and then take the loads of questions. I think this thing went on for over an hour. I had to leave because I had to go do one of these decision support calls to, I forget which entity it was, but I had to go over and do that real-time business, and they pressed on with this. But yeah, unprecedented level of engagement, decision support, and that allowed things to happen. So then we wait for the CMEs to arrive, and lo and behold, they showed up in mass. So you know how to read this chart a little bit now. Remember I told you 5 nanotesla? Well, look, now the chart scaling had a change here. 100 is the top number instead of, say, 5 or 10 here. This initially, when the CME arrived at Earth, or the batch of CMEs, the first batch arrived, it jumped things up to 7 times normal background strength. And that was the shock. Things escalated. You can see the red line is south. It stayed south almost the entire passage of this fleet of CMEs. Eventually, the field strength got up to over 70 nanotesla. So that's over 12 times the normal background strength. Incredible. And the deviation was almost entirely anti-parallel, meaning all that energy was going south as well and directly influxing into our systems. That's why you see G4, G4, G5, G5, G4, this load. That's why the world saw the aurora. It stayed connected like that through the entire event. And even if things came down and we wouldn't normally see a G3, we were still seeing G3s, even after the CME had mostly passed through, because things were so energized. It took a long time for things to settle down on all these things. Really quite the extraordinary activity and event that was going on. We continue to message all that information. We're doing the best we can. Remember, our primary focus is these phone calls, the sending out the warnings and alerts, doing the ad hoc or coordinated calls. It's not the social media and the messaging, but we did our best to try to throw all that out there, because it's really helped not only with the massive amount of press interviews that myself and others were involved with, but it also got you informed. It kept the sectors informed because they were using these posts as we put them out. I've come to learn how important these have become. Well, we reached G5, as you all know. We're continuing to message this stuff and press on. So this was historic storm, no doubt about it, but it was not the strongest. So how does this relate to other storms, everybody? This was a G5. If, you know, the G4 is my chin and the G5 is the top of my head, remember G5 is the top of the scale. You can have a G5 that's here, like this storm, or you can have a G5 that's 3 stories above my head, like the Carrington event. Historically, there's been ones that maybe even been potentially stronger. How do we know the difference here? Well, it's tough because there's been other changes, but there's something called the Disturbance Storm Index, which gives us a really good clue to comparison values. So this storm we had was very comparable to the 2003 storm. In fact, it may have been a little bit stronger, but it's certainly comparable. The 1989 storm, quite a bit stronger. That was definitely a stronger impact, because that was a minus 589 compared to minus 412 on the index. That's a substantial number difference. The Carrington event of 1859 seems to be on the order of minus 1200. That's the 3 stories up, everybody. That's the difference. But also, the reason 2003 was so impactful compared to this time was because the mitigation efforts. I guess I have that on that next slide. So let's talk about the known impacts first. There were impacts. There were plenty of effects. The difference I like to make is an effect is things people are seeing from the storm, but they can generally account for it. Impacts means either or, but generally it was something they can't quite account for as fully as they want to. So there were a lot of effects here. We talked about the LEO, the low Earth orbiting satellite community. Even geostationary satellites were struggling to maintain attitude and proper altitude in some cases because of some of the disturbances going on. The aviation community was diverting flights much further equatorward in the northern hemisphere than usual, so we'll just call it south, because of the aurora oval was so expansive, and that was disrupting their ability to communicate via HF radio. So they had to divert those flights much further south. It wasn't a safety issue as much as it was a communication need issue. The power grid operators were having alarms going off continually, voltage alarms, beep, 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 temperature alarms, whatever their noises they're making to these poor folks, they were having these alarms go off, but guess what? They were able to deflect, as some of the independent system operators did, to another transformer. So the overheating transformer could settle down. Extraordinary that they were able to do that. They weren't able to get that information in 2003. Other countries around the world are doing this space weather business now as well. I think that's why we're not hearing about worldwide impacts either outside of this country, because they're mitigating the issue too. They're using our information, their own forecast, their own information, and industries are becoming aware. We're an internationally connected world anymore. It's very important that everybody kind of behaves the same way. So here's what happened. The spectacular won over the consequential, right? You all got to observe and view the extraordinary aurora that we're lucky enough to be cloud free and out there. I didn't get the chance of a lifetime because I was doing my job, unfortunately. So I didn't get that wonderful chance. But this was the most successfully mitigated extreme space weather storm in history. I think we can safely say that at this point. It was the most prepared for because of the last 10 to 20 years of work that started off this presentation with all the executive orders, congressional actions, bills, and working groups that have gone in over the last 10 to 20 years. Clearly, that work needs to continue to be done so we continue to have success stories rather than failure stories. Because in the National Weather Service, we don't ever want to hear about people dying in a tornado. That's why we issue tornado warnings. Unfortunately, we can't protect their home. We can't protect the building with a short-term warning like that, right? In space weather, we kind of have a little bit of that luxury. When everything comes together, we can protect critical infrastructure by letting them know, and they can prepare and take actions as they can, as long as they can keep up with this. But here's the danger. Even though you see that great post NERC feedback from a webinar we did with them, clearly people understood the significance of that event and how the mitigation efforts and information exchange help prevent some kind of failure. Department of Energy, the NERC folks have both told me that if that storm had been much stronger, and when I say much, I mean not too much stronger, they're not sure they would have been as successful fully mitigating the issue. If there had been a major heat wave going on at the time, stressing resources, already causing them to do mitigation efforts, and this had happened, they're pretty sure there would have been some consequential failure of some kind here, somewhere in the system, or certainly they may not have been able to keep up with it. So I'm not going to say we were lucky because we were prepared, but you can see how this could have been a different story if they didn't get the information, or this had been much stronger, or potentially a combined terrestrial weather event. How do you stay informed? You visit our webpage. That's the best thing to do to get the correct information. You got other sources out there to help you out. That's great. But if you want the real story of what's happening and the data to get to, you should go to our page because we're the nation's official source for that. You can be informed by things like the Aurora dashboard, other dashboards and things of interest to you as a general enthusiast community to explore and look at from different types of models, to include the geospace model, not the geoelectric model, which you see on the right, but the geospace model on the left is incorporated into some forecasting plots for you to help you think about heading outside and looking for the aurora. 3-day forecast you should always look to as we put that out twice a day to see what the latest forecast is. Breaking down geomagnetic storm forecast by 3-hour increments is not easy. It's not that reliable, but it's a guide, right? It gives you a general idea. You can see we're forecasting something from 93 million miles away. Very difficult to get the timing down within a 3-hour window. Forecast discussion goes into so much more detail for you to understand the underlying cause, or kind of maybe from time to time, eventually we're going to get the forecast to put more confidence expressions in there instead of just on our messaging. You get informed, you can get stuff directly to your email through product subscription services. It's on our webpage to subscribe to. Finally, just kind of as your last couple items of note, because Tanya asked for it, so I'll give it. And that's what's been going on the last few days. Well, massive sunspot groups, especially in the southern hemisphere, have been populating the sun. I put this post together today because it turns out yesterday has probably been the highest sunspot number since the year 2002 for sure, maybe even 2001. That sunspot number is calculated each day. We do it internally in SWPC with our equipment, but we're not the official number. The official number is the Solar Data Influences Center over in Belgium. And they put out a daily estimate as well. Their estimate showed 299. Either way, that's the biggest number this cycle and for at least the last 2 decades. So the sun's been busy this solar cycle, as you well saw, compared to that plot comparison from what we were originally was it being expected. And then what's been going on? CME after CME after CME. I'm kind of glad I'm not working shifts this week because it's rather difficult to analyze all these CMEs, especially when they're not clear, they're faint, they're going in different directions and not clearly a full halo of any kind. So this is just a sample of some of the CMEs our forecasters have been looking at. They inject them in the model. They either show a clear miss, like the one on the top Enlil model plot, or they show some flanking influences. This is it going to be a hit Earth or not hit Earth? Is it going to be the flanking edge or a near miss? Very subjective, very difficult when you're talking 93 million miles of travel time. So that's why I have a very difficult time as well. It's not just about, is it going to hit Earth and how strong it's going to be, which is already difficult as I'm showing you here. But what's the orientation of that magnetic field? We don't know till it's a million miles away. So we can put a G4 watch out or a G3 watch. We may have a complete miss. So far, we haven't seen one materialize. We've had this G2 watch out so far today, but they continue to populate and propagate out from the sun. So just continue to be mindful and watch that real-time solar wind. Watch for those initial warnings to give you a clue something's arrived. Maybe a sudden impulse warning is something you want to subscribe to. So you know, a CME actually arrived a million miles from Earth. So there's other things for you to use out there to help you figure all that out. And with all that, I think I have talked aplenty. So I'm happy to take your questions for you. You can reach out to me. I just ask that it be something that you really are in need for. You know, Tanya's been a great contact for me, keeping me informed. So just know that she's on it. She's checking things out. So either way, I'm happy to take questions how we can for the next 10, 15 minutes or so.
Alrighty then. Well, thank you for all that. That was really awesome.
That was really awesome.
I guess, Tanya, do you want to narrate the question that was in the chat? I know you put it in the chat.
Well, it's not just in the chat. It actually is posted already on the live. But we do have questions on Aurora dashboard. Since SWPC does not forecast Aurora, how the tools that are under Aurora dashboards have been determined? Like what is posted there? What are you trying to communicate, and what are your plans for collaborating with Aurora chasers on actually potentially updating the dashboard with tools that we find useful for the chase?
Yeah, thanks for that, Tanya. The Aurora community is somebody that I don't think was heavily involved in the original production of that Aurora dashboard. That was something that was pretty much dictated down from higher levels, that they wanted to have something out there for that community, but we just didn't have the time to do this massive integration process. So what you got right off the bat was the first hack. Now, as you probably have clearly realized from this briefing, that anything relating to the Aurora is going to be down here on the priority list, because we've got all this work to do with all this growing number of users and reliabilities of our information that need to take actionable measures to protect things and equipment and our way of life. But you're not gone from the picture. I've already been taking a lot of the feedback you provided, sent it to our information technology folks for incorporation in the webpage for discussions to improve them. We know that what's out there is very basic and minimal and not all that necessarily helpful, a lot of it. But we also don't want to step on the toes of the commercial industries that are having dedicated, tailored service to doing Aurora forecasts. We try to leave that realm to them. But the reason we have what we have out there and would like to improve upon is because a lot of that does relate to impact potential for some other things. Not to mention it can be a source for observation storm reports from the Aurora community. How far is the Aurora actually being visibly seen compared to on your phone? I mean, that's important to know for the Ovation model to be better, for instance. So we always appreciate your feedback coming from the Aurora community. You know how important you can be. You were able to attend Space Weather Workshop and provide a presentation. So just know your voices are being heard. I'm a great person to be that voice for you and in how as I can. That may not happen until we start working our way down to solar minimum again, everybody, I'm fortunate to tell you, because of the high priority and how busy the cycle has been. But we will get there. We will get there and have better tools and better ways to communicate things you want to see. And I have your list. I have not lost that list. If I lose that list, I will reach out and ask for it again. But it is there. And I'm going to make it a more priority here as we start to wind down from the solar cycle.
Yeah, that makes total sense. I mean, obviously there's other stakeholders that are a little bit more important, you know. I mean, I fly a lot, so it's, you know, making sure that airplanes are communicating is important. So I get it. Let's see, what's the other question we have? Do the DST and GW have any relevance to each other? So that's the gigawatts, right? Yeah, or hemispheric power, I should say.
Yeah, I'm really incapable of answering that precisely for anybody. The DST is really, I'm not going to say it's a subjective thing. I think there's a little more science to it than that, but it's nothing that we're basing anything off of yet in forecast operations and services. It's really about three different means of measuring. One is the AP index, the KP index, and then of course the space weather scale, the G scale. These other things we're using, and we're trying to figure out how we can use them. Is it going to be of value to produce some kind of better observation? Is it something to help substantiate something when it comes to the KP index and the numbers that we're estimating? I don't know. This is all science that's going on behind the scenes and studying. But as of now, and that DST index has existed for some time, that disturbance storm index, it's of great value to give you an idea of historical comparisons, but as yet, nothing's come forward saying it would be an enhanced capability as a relationship to, say, some kind of voltage buildup on the high voltage transmission lines or the intensity of the aurora. But they are looking at those relationships. So eventually down the road, maybe there will be a capability to answer that question fully or find out that, yes, we can incorporate this and should incorporate this into one of our geospace models or our Aviation model or whatever the case may be, or even perhaps our forecast or alerting system.
Alrighty. And then one more. Is there a prediction of when solar max will wind down?
Wow, good one. Kind of, right? That's that solar prediction plot, the modified one. If you look at that, or even the one that's currently on our webpage as the considered operational one, it gives you an idea of when it's going to, the kind of expectation based off normal curves and normal activity levels of when that might wind down. I don't know how much science is into that at this point, but either way, that's the indicator. So there kind of is an idea, but I don't think it's anything official. Solar minimum won't be announced until we've kind of passed solar minimum. They'll say, okay, this was like solar minimum for solar. The last solar cycle was December of 2019. Solar minimum marks the beginning of the next solar cycle. So that immediately means we're moving into solar cycle 25. So yeah, I can't answer that because I don't know the answer to that. But yes, that curve does incorporate when that's going to be. And just remember, solar max, doesn't shut off, right? It's a strong curve. It's usually quicker to rise and then slower to come down. So the thing to think about here too is all of 2024, because we still don't know if we're reaching peak or at peak. That could be anytime this year to early next year. They'll figure that out based off these trends and numbers. Clearly, we're still climbing up in sunspot numbers. So we don't think we're there yet, but we don't know for sure. That's up to the bigwig scientists to figure out. But either this year or sometime next year. But all of 2025, well into 2026, we're still going to be at, as unlikely it is, an increased risk, a better risk for one of these severe to extreme storms again, because of the way the sun works. Those sunspots, they migrate as the solar cycle progresses. Not all of them, but in general trend is that they line up closer to the equator as a solar cycle maximum happens and continues down. So they'll be in a prime position for potential CMEs to erupt directly facing Earth as full halo events as the cycle continues, even as it begins to wind down. So this is something that concerns me for our missions back to the moon because of those radiation storms, CME potential. We've already had a G5. We're not even necessarily know if we're at the peak yet. Some of these historically in the past have happened as we've been on that downward trend. So we've got a ways to go here in this cycle. It's been exciting. It's been active. The communities are learning a lot more. Industries are taking actions. They're testing their actions if they have plans in place because this cycle has allowed them to do that. So we can only get better at this in the long run.
Yeah, that sounds good. Kind of on that note with astronauts, are you thinking like delaying stuff till solar minimum because of the CMEs, or because I know that solar minimum it tends to bring in more cosmic rays. So you're really never free of radiation storms. So I'm guessing it's just kind of like a risk assessment, like, hey, maybe we'll do this during solar max instead of waiting because of the, I was just kind of curious the thought process behind that in terms of like the moon missions and things.
Yeah. Um, no, I certainly don't know the answer to that at all, but
Yeah.
there's a lot of things that go into those launch planning and timing, and it has to do with orbital mechanics. It has to do with money, what
Yeah.
budget's available, when it's available, training, equipment issues or not issues. Is a platform ready or not ready? What's the earliest we can go up? What's our slide on the schedule availability? And it's all important to get it as right as possible for just going to the moon, right? Because eventually we want to go to Mars. And that's where, when you're doing long range planning, these orbital mechanics and timing really become an issue because you have to go at certain times to make a shorter travel time to Mars, right? Not necessarily with the moon as much. But all these things go into this stuff. It's all beyond my head. But it's an accepted risk. But it's one that they're willing to accept because they know they can. The likelihood of an extreme solar radiation storm that could be harmful to astronauts is very, very low. But even at the lower levels of activity, they're going to have adequate plans in place that will allow the astronauts to avoid the less shielded areas of the capsule, to even go to measures where they would actually change their positions in the spacecraft and kind of shield themselves by pulling some equipment around them or being into an area and moving some things here or there, because every little thing they can put between them and the exterior of space is important and really brings down any potential radiation exposure. So that's where the experts at NASA, Space Radiation Analysis Group, are doing their work to prepare for that kind of thing. And then our job is just going to be to do the best we can predict these events. But something new for us is really going to have a stronger handle on the duration of an event, because these actions are going to have to do, it's going to limit their ability to operate within the capsule in the most worst case scenarios. And they got to be able to operate that equipment. They have to be able to step outside of their shielding, kind of in place shielding a little bit. And I make it sound like it's a vast space. Their space is going to be extremely small, right? There's not a lot of room to move around in there. So anything they can do to help them out is going to be a help. So that's one thing, is kind of an all clear. When are things safer to start moving around that we'll be involved with. But we're not the decision makers on that. That's all the big experts at NASA and their associated support. But we'll be the voice for the forecast and any watches, warnings, and alerts for all of that.
Awesome. Well, thank you. I wonder, do we have any more? Are we good? I think we're good on questions. But yeah, this has been amazing. I love learning all this stuff, like all the things behind the scenes and how much work goes into this. Like we were joking this whole week that I don't envy anybody in the space weather forecasting right now. I just don't.
It's very very tedious, banging your head sometimes. I mean, think about the sunspot number. Every day we have to produce a product that is more of an observational science summary, but we do it as part of our forecast thinking as well. So it's a necessary step. But we classify each of these regions. I talked to that a little bit. The amount of time that can take when you have such an amount of sunspots in the sun, in between your other tasks or having to get distracted, you got to send out the alert here and make these phone calls. You can lose track, and it can be so quick and easy to make an error on a position, or am I looking at region 3770 or 3770? Yeah. So, there's a lot of patience involved in double checking our work, triple checking our work to make sure we're not losing track of where we were at, where the defining line is in a group, because sometimes they become clustered together and you have several different groups that look like one. So yeah, it can be frustrating, difficult at times, but we all enjoy the challenge. We all enjoy this work. That's why we got, a lot of us came from terrestrial weather backgrounds and mainstream meteorology. So we can make quick decisions on the fly with limited information, but it's still, you could be a lot more correct in terrestrial weather than you can be in space weather. So you got to be able to take a beating along with the success stories. But that's, it's always a challenge, and it's a good thing to keep things smart and keep research to operations and operations to research efforts going.
I love it. Yeah, and I really enjoyed being like as like just a I don't know, citizen science, like with all the Aurora stuff. It's been really cool to be kind of a part of this world and being able to contribute to things. Cause I don't really have a science background, and it's neat that, hey, a picture that I took could be used for research. It's been really fun. So, and it's fun to, it's really great to talk to people that work in the industry, work behind that we look at this stuff every day. So it's just really cool. So I appreciate very much you taking the time to be here with us. It's been great. I'll give you a little heart.
Hey, all right. Thanks for that. Been my pleasure. Like I say, we're always happy to when and how as we can to help the general public, no matter who you are, where you're working with, or what you're doing as a hobby.
Yeah.
Because getting everybody, we take great pride in the Weather Service for having a weather ready nation. Well, we want to have a space weather ready nation too. So thanks for what you do as well.
Yes, thank you very much. So on that note, I'll end the YouTube live stream. So everybody watching, thanks for watching. And this will be available. What was that? Oh yeah.
Stream.
Oh yeah. And then me and Christian are going to do a little debrief stream after this too. So we'll still be doing this. But yeah, thank you again. Thank you so much. I appreciate it. I'm going to give you the, yay.